All right, guys, STAT1800, more on confidence intervals. We're focusing on one specific type of confidence interval right now. And the interval we're looking at is where we have an unknown mean, mu, population mean that we want to estimate, where kind of a rare situation where you would have that the standard deviation is known. Sorry, I'm out of breath. I just finished a workout. And I should have waited a couple more minutes before starting this, but oh well, it is what it is. Guys, a couple of things about confidence intervals. What do they do for us? As I mentioned in a previous video, they can be used to estimate an unknown population value. And this is called a parameter. So when we have a value from a population, it's called a parameter. So we can estimate an unknown parameter value from a population. We can also test a claim about a population value. Okay, now in this week's instructional videos, I have uploaded a handout, and I think, guys, don't hold me to this, but I think I called it handout Z intervals. I'm pretty sure that's what I called it. So what I want to do is I want to work through that with you. This is, I think, the opportunity for you to learn best is when we actually work problems, and you know, I work the problems for you and talk through what I'm thinking. I think we call that teaching. I don't know. Who knows? But I've already got this printed out, so you may want to grab it. But again, it's in this week's folder of instructional videos. Now, guys, we're going to run into all kinds of different confidence intervals, but the kind that we're examining right now are specific to this criteria. The unknown population mean is what we're trying to estimate or test a claim about, and the population standard deviation is known. When you have that, we call this a Z interval. In fact, you can I know a lot of people, I don't require these anymore because they got so daggone expensive. But a lot of people have them from high school. Let me get this where I can see it. If you go to your stat key and go over to test, you can see that you have a Z interval that you can use your calculator to construct. Again, I use StatCrunch because I think it's easier, and it's included in my stat lab. So, all right, gang, let's grab the handout. Mine is here someplace, I'm pretty sure. Yeah, here it is. And let's work through this together. All right. So the first one says a paper manufacturer has a production process that operates continuously throughout an entire production shift. The paper has been shown to have a particular mean length of 11.0 and standard deviation 0.12. Now let me tell you, let's stop right there. What am I thinking here? They just made a statement about the paper, all paper. So I see this mean length here as being a mu, and the sigma being 0.12. And guys, both of these are measured in inches. You'd like to use a confidence interval to test if the mean length is still equal to the 11, or if something has gone wrong in the production process that has changed the length of paper produced. So when we go back to what I told you back here about the two applications of confidence intervals, we're actually doing this one now. The production process is supposed to create a paper length of 11 inches. We want to test that claim to see if our paper process is still working as it should, and we're going to use a confidence interval for that. Now, as we read the second, what you would expect in general is we would next want to take a sample. All right, so the next paragraph says to carry out the analysis, you take samples of paper at periodic intervals and measure the paper length of each. You decide to take a sample of 100 sheets. So, guys, I know my sample size is 100. The sample mean for these 100 sheets is 10.998. So since that's a sample mean, it uses notation X bar. And a sample standard deviation, so that's going to be Sx, is 0.18 inches. Now, construct a 95% confidence interval to estimate. Okay, construct a 95% confidence interval, and that should be to estimate the population mean paper length. Okay? So guys, remember the sample, the confidence interval formula that we know right now is this. My X bar is what I get from my sample, so that's 10.998. We're estimating at 95%, so the Z critical is 1.96. My sample standard, or my population standard deviation. Since we know the information of the population, we use sigma here instead of the sample standard deviation. Now, there's a rule in statistics that sigma always trumps the sample standard deviation. The population standard deviation always trumps the standard deviation of the sample. Now, starting next video, we're going to look at more realistic cases where the sample standard deviation is all that's given. And I'll get into that later in this video. But for right now, we've got a claim about all paper sheet lengths. So we use the population standard deviation of those lengths instead of the sample standard deviation just for these 100. The reason? This is stable. This is a statement about all sheets, or at least what's supposed to be going on with all sheets. This is specific to these 100, which we know would change from sample to sample. So we want to use the stable measurement if we have it available. Sample size here was 100, so over the square root of 100. And you could easily use your calculator to calculate this confidence interval, but I'm not going to do that. I'm going to do this problem the way you would probably do it. So I'm going to go to STAT. I'm going to go to ZStat one sample, and I have width summary. All right. So my sample mean is 10.998. My standard deviation, again, guys, always use the population standard deviation if you have it. If you don't have it, I'm going to teach you what to do in the next few videos. Sample size is 100. And I want to do a confidence interval, and for now I want to do a 0.95. All right. I do that, and the last two numbers are the left and the right endpoints of our confidence interval. So guys, I'm going to write that down. Our left is 10.97. Our right is 11.02. All right, so go back over and I've written the confidence interval there. Now what we did, we're kind of concerned whether our manufacturing process is still working at consistently at the 11-inch length that it's supposed to. Well, this confidence interval, we're 95% sure there's a 0.95 probability this interval contains the length, the average length of the sheet of papers. Since 11 is contained in that interval, I feel confident that our current manufacturing process is meeting the standards by which was outlined by the makers of the I guess the paper cutter, I guess is what's actually going on here. So it seems like to me, based on this, since 11 is in here, that everything is working as we would hope it would be. Question number 2. The operations manager at a compact fluorescent light bulb, CFL, factory needs to estimate the mean life of large shipment of CFLs. The manufacturer's specifications indicate the light bulbs have a mean life of 8,000 with a standard deviation of 1,000 hours. So guys, from this right here, I can see that the mean of all bulbs is 8,000 and the standard deviation of all bulbs is 1,000 hours. Now, just like the previous example, it looks like we want to test it out. So we collect a random sample of 64 of these bulbs, we plug them in, we see how long they last, and we see that their sample mean life is 7,500. So we want to use information from our sample to see if this large shipment is maintaining the standard that's indicated by the manufacturer's claims and specifications. So now when I read the second paragraph, I see 64 of these, so I know that n is equal to 64. Sample mean was 7,500. And the sample standard deviation was equal to 1,200. Guys, this information right here is meaningless to me. It's meaningless in this problem because I have a value that's more important to me. I have the population standard deviation. This trumps this. So if I have the population standard deviation, I ignore the sample standard deviation. Now, let's just for an exercise in practice, let's run through what so we're doing shifting things a little bit here, doing a 99%. So again, guys, it doesn't change. X bar plus or minus Z critical over sigma divided by the square root of n. So X bar is equal to 7,500 plus or minus the Z critical is 2.576. Sigma is 1,000. And the stand, let's see, we have 64. All right, let's go to StatCrunch and do it. A student one time said, well, how do I know I'm supposed to go to ZStat? You're not supposed to know that. It's my job to teach you. It's your job to watch these videos thoroughly and entirely, and sometimes multiple times, to give me the opportunity to teach you. All right? So ZStat, one sample with a summary. All right, so the sample mean looks like, again, 7,500. Population standard deviation is 1,000. Again, we always use it if we have it over the sample standard deviation. You guys need to adjust this to 99 instead of 95. And that's it. So my lower limit is 7178.02 and my other is 7821.98. So my lower limit and upper limit are given in my table in the last two values. Now going back to the original problem. Specifications by the company, by the makers of these bulbs, claim they'll last 8,000 hours. The evidence from the sample that we took from this large shipment indicates to me that either they sent us light bulbs that aren't up to standard, or there's a concern with their claim about the manufacturer's specifications. And guys, this process, as simple as it is solid. I mean, this could be taken into a court of law and be used as evidence against some sort of maybe tampering with the specifications, or maybe when they first started producing these light bulbs, they did last this long, but something's happened in the manufacturing of the bulbs that's decreased the number of hours these things last. But anyway, there is statistical evidence, strong statistical evidence, since this entire interval falls below the claim of 8,000, there is statistical evidence that these light bulbs aren't lasting as long as the manufacturer specifications seem to indicate, or not seem to indicate, do indicate. Guys, very powerful tool. You know, again, it's very simple. Once you can get the notation clear in your head, understand kind of the foundation, plug this thing into some sort of technology, the confidence intervals are extremely easy to find. Now, just as a just to, kind of as a review, remember the margin of error would be found by taking the big number minus the small number divided by 2. I'm just going to plug that in the calculator here very quickly. So 7821.98 minus 7178.02 divided by 2. So it looks like the margin of error is 321.98. Now this thing can also be found, remember the margin of error can also be found by taking the Z critical times sigma over the square root of n. This way is much easier, but this way goes back to something I pointed out in a previous video. So for the 99, we could use 2.576 over sigma, which is 1,000 over the square root of 64. And if you put that in your calculator, you're going to find out that you get the same thing here that you get this way. I just think this is much easier. Just high number minus low number divided by 2. Third question. Guys, we're learning. Fun stuff, right? Number 3, how would the previous problem change if a 95% confidence interval was calculated instead of a 99% confidence interval? Well, the reason I want you to think about the margin of error calculated this way is leading up to this problem. There is a method to the madness. Now, if we were to calculate a 95% confidence interval versus a 99% confidence interval, this part right here would be the same. It's irrelevant. The population standard deviation divided by the square root of n would be the same regardless whether it's this or this, 95 or 99. But this changes. If I have a 99% confidence interval, the number I'm going to use right here is 2.576. If I have a 95% confidence interval, the number I'm going to use right there is 1.96. What happens when I multiply by a bigger number? I get a bigger margin of error. So the 99% confidence interval is going to result in a larger margin of error than the 95%. So with 99% being the one that we calculated, by changing to a 95% confidence interval, we are going to decrease the margin of error. We're going to decrease the width of the confidence interval. All right, number 4, a market researcher selects a random sample of 100 Twitter users. Guys, if you want to follow the most boring Twitter user in the history of Twitter, follow me. I tweet about, well, I don't know how much I tweet. I don't tweet much. Maybe once a month. And that may be stretching it, but anyway. So if you want to follow the most boring Twitter user ever, my daughter follows me and she doesn't hesitate to tell me how boring I am. But anyway, so we have a population of over 100 million accounts. Well, I didn't realize that. After analyzing the sample data, she states that she is 95% confident that the mean time spent on the site per day is between 15 and 57 minutes. Explain the meaning of this statement. Well, what you can say is if you took all the possible confidence intervals and calculated them, so you go in and you take a sample of 100 and create the confidence interval. Go in again, take another sample of 100, create the confidence interval. Just keep doing that over and over and over and over, forever and ever and ever. So you have pretty much infinitely many confidence intervals that have been created. 95% of those would contain the true well, there's a 0.95 probability that well, 95% of them would contain the true mean value, mean time spent on the site per day. So for the specific one that they have calculated, she has calculated from 15 to 57, we can just say that there's a 0.95 probability that the mean time spent on the site per day is between 15 and 57. B, is it true that we do not know for sure whether the population mean is between? Yes, it's true. There's a 0.95 probability. That's not 100%. That's not a probability of 1.00, which means we've got it for sure. We're dealing with a sample, so we run into situations where there are errors. So is it true that we do not know? Yes, that's true. We do not know. Is it possible to determine the sample mean from the information that is provided? Yes, it is. Because, guys, remember, what happens in in calculating a confidence interval is we start out with the sample mean, and essentially we add the margin of error to it to get the top value, and we subtract the margin of error to get the bottom value. Well, what resides right smack dab in the center of the interval? The sample mean, right? So if we know that this value over here is 15, and this value up here is 57, then what's the easiest way to find the number that's smack dab in the center? Well, take the average of them. So I'm just going to take 15 plus 57 divided by 2. What's smack dab in the center of that is 36. So I know that the 100 Twitter users that she used as her sample spent 36 minutes, average on Twitter per day. And again, because this is one sample of infinitely many, and we know these samples vary, we have to build margin of error around this value to estimate mu, which is the mean time spent for all 100 million, or actually over 100 million accounts. Is it possible to determine the population standard deviation from the information that is provided? Yes, it is. All right, so what do? We start out with our formula. So we know from our previous calculation that the mean had to be 36. And guys, I'm going to stop right now and tell y'all something. You've got to get in your head, you've got to tattoo this to the brain, the difference between mu and x bar, sigma and s, the notation for population mean and sample mean, notation for population standard deviation and sample standard deviation. You've got to tattoo that to the brain. You have to know that. That almost has to become second nature to you. This is the sample mean that corresponds to the 100 Twitter users in our sample. The population mean for all over 100 million accounts is mu. Okay? And we are dealing with the type of confidence interval where population standard deviation is known. Okay, so she said that there's a 95%, so we know we have to use Z critical for 95%. We don't know that, but we know that the sample included 100 Twitter users, so the square root of 100, I'm just going to go ahead and simplify that and put equal to 10. Now, how does that help me? Well, I know that the end values were 15 and 57. So I can choose either one of these, the plus or the minus. If I go 36 minus 1.96 times, that has to be equal to 15. If I go 36 plus standard error, well, the margin of error, it has to be 57. So 57 has to be equal to 36 plus 1.96 sigma over 10. Now, I'm going to have to do a little bit of algebra here. That's fine. Subtract 36 from both sides. So I get 21 is equal to 1.96 sigma over 10. I'm going to divide both sides by 1.96. So I get 21 over 1.96 equals sigma over 10. I'm going to multiply both sides by 10. So sigma has to be 10 times 21 over 1.96. So 107.1429 is what I get. See what I did there? All right, let's test it out. Stat, Z-stat, one sample with data. Let's see what happens. No, come on. Stat, Z-stats, one sample with summary. I don't have my 100 numbers. We're claiming here the sample mean was 36. We're saying the standard deviation was, I'm going to multiply this out, 10 times 21 divided by 1.96, because I want the entire standard deviation to be in there. And the sample size was 100. And I want a 95% confidence interval. 15 to 57 when we round off. So guys, everything turns out perfectly. Cool. We like perfectly, don't we? It's kind of embarrassing if we don't get perfectly. All right, next question. Number 5, you're assigned to work as an assistant to a dean of institutional research. I think what they're wanting to do here is learn more about starting salaries. So you take 100 alumni. You can pause me and read this more carefully. Earning their baccalaureate degrees, constructed, and all provide their starting salary. Can we use the following formula to construct a 95% confidence interval? No. I got information, X bar, so I can take the starting salaries of all 100 alumni and I can divide by 100 and I can get the mean for these 100 people. That's cool. I can always get Z star for the 95%. That's fine. Sample size is 100. That's cool. But guys, I don't have anywhere in the problem where I know sigma. So no. No can do. Sigma is not given. Guys, finally, can you ever know the population standard deviation? Yes and no. Sometimes. But very rarely. In fact, it's almost unrealistic to think that you're going to get many situations where the population standard deviation is known when you're trying to estimate the value of mu, which is unknown. So the criteria here, mu is unknown, sigma is known, Well, how can that be when sigma is nothing more than the square root of the sum of all the values minus mu over the degrees of freedom? Well, in this case it would be n. Sigma is calculated by knowing mu, but yet we're coming up here with the assumption that mu is unknown. Now, sometimes that happens, but again, it's very rare. When you're taking a subset of the population that was used to create this, again, look at a value, something we did earlier. IQs of everyone, normally distributed with a mean of 100, standard deviation of 15. But what if I want to come in and just look at the IQs for nurses in Ohio, as I did in a previous video? Well, I can still use that population standard deviation, but nurses go through a lot of training, so it is reasonable to think that the mean IQ for all nurses in Ohio is going to be higher than the average IQ for the general population. So I'm coming in this larger population, and I'm pulling out a particular subset that I want to examine. In cases like that, it is reasonable that the population standard deviation is known. However, let's say that I want to just come up with, maybe I want to know mu, which is the mean wait time at Tim Hortons. Now, I don't know anything about mean wait time at Tim Hortons. They seem to be pretty prompt and pretty accurate to me. I love their coffee and bagels, but I don't know anything about the population standard deviation. So things like that, much more realistic, where you're going to run into situations where you don't know the population standard deviation. Well, guys, we're going to learn something called a t-interval in the next few videos that we're going to use to address problems like that. So, guys, I'm done. Have a good one.